Good afternoon. Welcome everyone to the online Geneva Trade and Development Workshop, which is a seminar series jointly organized by the CEPR, the Geneva School of Economics and Management, the Graduate Institute in Geneva, UNCTAD, and the WTO. For today's seminar, I'm delighted to introduce Esteban Rossi Hansberg from the University of Chicago, who will present the economic geography of global warming. The presentation will last an hour and will be followed by 15 minutes of questions and answers. During the presentation, please feel free to ask clarifying questions in the Q&A window. I will try to relay them to Esteban with the help of my co-hosting colleagues. So without further ado, Esteban, the floor is yours for an hour.
Thank you very much for the introduction. Let me share my screen. Okay, so hopefully you can see that. So this is, I should say that this is joint work with Jose Luis Cruz, who is a student at Princeton that will be on the market this year. So, remember him. And so what we're trying to do in this paper, or more broadly kind of the agenda that we have, is to try to think about and developing assessment models to evaluate the consequences of climate change. And in this paper in particular, we want to think about global warming. What are the implications that the world is warming up, and in particular, different regions are warming up at different levels, and what are the consequences that this is going to have on the economy. So we want to build this type of assessment models. And in order to do so, we need to take into account some of the key, or what we think are the key characteristics of this phenomenon. The first one is that it's a very protracted phenomenon. So even though we're already feeling some of the implications or the consequences of global warming, there's, those are going to develop over many years, decades, even, centuries. And so we need to take that into account, the fact that, this is developing relatively slowly over time. The second one is that it's a global phenomenon in the sense that whatever one particular location or firms and individuals in a particular location do affects everyone in the world. In this case, the carbon emissions in particular locations by particular firms mix very quickly in the atmosphere and lead to changes in the global stock of carbon, which is what actually affects global temperatures, and in turn local temperatures as well. And then finally, this phenomenon is going to have very heterogeneous effects across locations in the world. So very heterogeneous local effects, meaning that a particular increase in temperatures in average temperature in the temperatures in the world is going to imply different increases in local temperatures first, but second, an increase in say of 1 degree Celsius in a particular location that doesn't have the same effect than in another. So if temperatures increase in a very cold location, that's of course very different than if temperatures increase in a very warm location. And so we want to try to take all of these important characteristics into account in building these assessment models. And in doing so, we want to produce a model that is kind of properly micro-founded. And in that sense, it's kind of a modern economic assessment models where there's individuals and there's firms that are making decisions, and by making those decisions are reacting and adapting to this phenomenon. And of course, if you want to emphasize this heterogeneity in the local effects, that also emphasizes the ability or the possibility to react this to warming by changing location or by changing trade specialization, etc. There's different dimensions in which individuals that are making decisions can adjust their behavior in order to deal with this phenomenon. Okay, and so we're gonna propose, or I'm gonna show you the kind of the type of model that we're proposing. We're gonna quantify it, and then I'm gonna try to give you some idea of what the model implies and what are the implications of policy within such a model, and that those are gonna, like I was saying, emphasize adaptation through a number of channels. In this particular paper, I'm going to talk about adaptation through migration, so changing locations, trade, and innovation. So the fact that firms can decide to invest in particular locations, and that can develop those locations and make them better places to produce, which we think is an important channel through which the economy is going to adapt to climate change. Okay, so there's a literature that is building up quickly on these topics. There's and here I just classified it in four bins, if you will. And the first bin is a set of papers that has tried to study empirically what are the implications of changes in different dimensions of climate. And so this is just trying to relate those in a statistical way and try to establish the causality of climate into some form of economic damage. But there's no model of individual behavior behind those assessments in general. Then there's models that have tried to build full economic models of climate change, and there's many of those. Of course, Nordhaus won the Nobel Prize for them, so he has been a pioneer in building this type of models. But by now many others have joined this effort, and I have a list of many of them there. Most of those studies have emphasized the dynamic aspect, this protracted aspect of climate change, rather than the spatial heterogeneity, although some of them have done that too. And then there's a set of papers that have emphasized or have tried to develop spatial dynamic models that have not been concerned with climate in particular, but have developed kind of the core methodology that can be used to think about processes that have both an important time dimension, but also this an important spatial dimension, as is the case with climate change. And then finally, the ones that have incorporated climate into those. And so we're very, very much in that final group, and trying to push the idea that you really need to develop these theories and these models to try to build modern economic assessment models of this phenomenon. Okay, so part of the way we're going to do this is we're going to take one of these kind of more methodological papers about developing spatial dynamic models. In particular, I'm going to take one that I developed with Klaus Desmet and David Nagy in the JP in 2018. That is going to form the core of the economic mechanism that we're going to use in order to evaluate the effects of global warming. And so, this diagram kind of gives you in a very simplified way kind of the elements of the model, and then I'll go into some detail into particular parts of the model so that you understand some of the details a little bit better. Okay, so think about a world that is formed out of many locations, and there's individuals and firms in those locations. The individuals own, can supply labor, own land. Firms are gonna use those inputs to produce particular varieties. These varieties they're gonna trade with other parts of other firms in other locations potentially. And these firms are going to have the option to innovate And by innovate, I mean they have the option to pay in order to improve their technology. Okay, and so if they do so, then their productivity is going to be better, which is going to allow them to produce potentially at a lower marginal cost. Okay, and so that's in turn going to determine the wages and rents that they can pay in wherever they are, and that together, and those wages and rents together with the local amenities, the local characteristics of how nice it is to live in a particular location, are going to determine whether an individual wants to be there or wants to migrate somewhere else, subject to some migration cost. Okay, and so that core of the core economic model is what is represented in black in this chart. And then what we're going to do in this paper is we're going to add everything that is in green around it, right? So these are the elements that we're adding here in order to adapt, in some sense, the model to this phenomenon of global warming. So the first thing that we're going to do is we're going to add energy as an input in production. And so now labor, land, and energy are going to be the inputs. And energy, in turn, can be produced using either clean energy or fossil fuels. And if you use fossil fuels, then that's going to lead to CO2 emissions, which in turn are going to affect the stock of carbon in the world, which in turn is going to affect global temperatures. And all of that is going to happen through a standard carbon cycle that we're going to borrow from the IPCC. And then that change in global temperature, in turn, is going to map into changes in local temperatures. And these changes in local temperatures are the ones that are going to affect the economy, the local economy. Okay, so these changes in local temperatures are going to affect the local economy in three different ways. The first one, they're going to affect productivity, so the productivity of the firms operating in that location. They're going to affect amenities, so how nice it is to live in that particular location. If it gets very warm, it may be inconvenient to live in a particular location, or just not pleasurable. And then the final way in which they're going to affect local characteristics is they're going to affect natality rates. So which I'm going to refer to as natality rates to the birth minus death rate in a particular location. So temperature can also affect that. For example, we have good evidence by Greenstone and others that the temperature can affect the mortality. Okay, so we're going to allow temperature to affect things in those three different ways, which in turn then is of course going to affect where individuals want to locate, how much firms want to invest and trade. Okay, and so that's the three adaptation channels that I was talking about. We're going to take this model, we're going to quantify it in a grid of the world that is 1 degree by 1 degree. We're going to use data on population and income. Our base year is going to be 2000 in order to inform the model and be able to back out what are the productivities and amenities in the different parts of the world. And then we're going to, parameterize trade relationships so that they satisfy standard gravity equation. So in that sense, we're going to be close to matching trade flows. And then finally, for mobility frictions, we're going to choose, and I'll go into more detail on this in a second, we're going to choose mobility frictions such that the model can exactly replicate the changes in net population between 2000 and 2005. Okay, so that's kind of in a nutshell the way we're gonna do this. Now let me go into a little bit more detail into some of the parts of the model. So the first is preferences. So there's intertemporal preferences that are additive over time with some discount factor. And now let's think about the period utility, the one individual period utility, and we're going to talk about an agent at period t, agent I, that has a history of where she has been, that I'm going to denote by that r bar minus. So this is kind of all the vector of all the places where this person has been, and it's today in location r. Okay, so this is the period utility of such an individual. And so what are the sources of that utility? Well, the first is consumption. And so she's going to consume the different varieties that are produced in the world. It's going to be all aggregated using a CS utility function. So that's kind of standard. The second part are the amenities. The amenities are going to have two components. Let me talk about the second component first. That's just an idiosyncratic component where, you know, different individuals may like different locations differently, depending on, you know, I don't know, where they're from or their family or whatever they happen to like. And that's going to come from, as is standard in these spatial models, from a Fréchet distribution. And it's going to be a source of congestion in these models, right? These idiosyncratic preferences are a source of congestion in the sense that, you know, if we want to pack a lot of people in one particular location, the marginal guy likes that location idiosyncratically less and less the bigger the location, okay? And so because of that, this is a source of congestion. And, you know, in fact, that's governed by the parameter of that distribution of idiosyncratic preferences, how fast, you know, that declines as you increase a particular location. So that's a source of congestion. Then the second term, that B that I have in green, right, is going to have some components. And the reason it's in green is because that's where climate is going to have a role. Okay, so we're going to separate that B into two pieces. The first is one local congestion effect. So this is something that everyone experiences. So that B is common for everyone, right, in that location. And so the first part is that it's going to be determined by, there's going to be a congestion force, so that if there's a lot of people in one particular location, say in location R, right, people are going to like it less. So you know, if there's lots of migrants coming, they crowd everything, people are going to like it potentially less. How much less is going to be governed by that parameter lambda that I have there. And then the important part for us here is that it's also going to be determined by climate or by temperature, I should say, through this damage function. Okay, and this damage function, what it does is we're going to allow it to depend both on the level of temperature and on the change in temperatures. Why? Because, of course, you know, the change in temperature, as I was mentioning before, it's going to affect different regions differently depending on whether they're very cold or they're very warm, right? And so we're going to allow for that. And we're going to estimate that damage function in a second. I'll show you how we do that. But for now, just it's important to understand kind of how this is going to get into or into the model. Okay, so that's that. And then the final part is this migration cost. So the way we are thinking about migration cost is as follows. Think about, you know, I was born in Mexico, then I moved to the United States. And so the way this is going to happen in terms of migration cost is the moment I move to the United States, right, I start paying a flow of cost. And that flow of cost is that M function there. Now, if I then move somewhere else, right, I pay another flow associated to the next move that I'm making, and so on. And so in that sense, the history of all my moves is accumulating in these flows that I'm paying. Okay, now that's a complicated object. That's the object that I represented there with the product, right? Now we're going to make some important simplifying assumptions to deal with this, which are at the bottom of the slide here. So, and we're going to essentially make this assumption, namely that this is log additive. Namely, there's an origin effect and a destination effect, okay? So importantly, that rules a lot of things out, in particular kind of bilateral costs, right? So this is an important simplification, but of course it simplifies that complicated product in a way that makes our lives a lot simpler, because together with the basic assumption that if you stay in the same location, you don't pay anything, this implies that when you accumulate these flows, say I go from the US to, from Mexico to the US, and then from the US to Germany, right? The moment I move from the US to Germany, the US piece is gonna cancel out, right? And the only cost that I'm going to be paying is as if I had originally moved from the Mexico to Germany. Okay, and so that's the flow that I'm going to be paying. Okay, so that simplifies things, but importantly, is not going to restrict the ability of the model to match the changes in population over a particular period of time. As I was saying, we're going to use the change in population between 2000 and 2005 to calibrate this cost. And these assumptions don't restrict our ability to match those exactly. So if the only thing that we care about is how population is changing in different locations in the world, this is not restricting the ability of the model to do that, okay? So that's why we're using, but it simplifies the structure of the model and the ability, and allows us to solve the model because it makes migration reversible. The only thing that I care about is the cost of where I'm going today. I don't have to do this future expectations of what's going to happen later on, okay, in order to make my migration decisions. Then the natality piece is just saying, you know, whatever the number of people are in a particular location, you know, the natality rate is going to imply that tomorrow, or, you know, in the morning of next period, there's going to be 1 plus that rate. And in that particular location, and of course, where those people are matters because it determines because of the migration cost, right? Because, you know, people, because of the migration costs, are going to tend to stay where they are, and so where they are born matters. And eventually, I'll show you the specification of that n later on. But we're going to make that n a function of local income and temperature as well. So, you know, to reflect some of the Becker type quantity quality trade-offs in fertility decisions. Okay. So, and then the last part that I'll describe in some detail here is the technology. So think about a firm producing a particular variety omega in a location R at the time t. Okay. So this is, and I'm gonna divide everything per unit of land. So I'm going to divide by the units of land already. So everything in this equation is already per unit of land. Okay, so this is important. And so the technology is Cobb-Douglas in the three inputs, land, labor, and energy. I already divided by land. And so it's going to be decreasing returns in labor and energy, right? Now, that is another congestion force. The fact that firms use land is in fixed supply, right? And so that's a form of decreasing returns, which is another congestion force. It's hard to make lots of people going to the same location. So I already gave you 3 different congestion forces. We're going to need some agglomeration forces as well, of course, which I'll introduce now. Okay, so there's the these 3 inputs, and then the first 2 terms are the productivity of this firm in that period. So I separated it in 2 pieces. The first piece is innovation. So that's the firm is going to decide how much to innovate, subject to a cost that is also going to be a power function. And so it's deciding this fee, how much it wants this fee to be today. And then it's drawing, as is again standard in like Eaton and Corton type models, is drawing a productivity, or I guess in Mellitz, is drawing a productivity draw from some distribution. And that distribution, or the level of that distribution, is going to be governed by this parameter A, and that's where we're going to introduce the effect of climate. Okay, so first, we're going to allow for a local agglomeration effect governed by that parameter alpha. So more people in a location make the level of that distribution higher. And we have plenty of evidence that, of course, there's a kind of agglomeration effects in cities and etc. So that's trying to capture some of that. And then the more important part for us, or for this talk, is that climate is also going to affect that A. And so it's going to affect that A through a damage function, the green one here at the bottom, that also depends on the level of temperature and the change in temperatures, very similar to the one that I discussed before for amenities. And so the level of this distribution of productivities from which firms are drawing is going to be determined by that the changes in levels of temperature, the abatement function that we discussed, plus these terms here at the bottom. So this is simply productivity last period, or the level of this productivity's last period. This is just the investment that these firms made. So these investments are going to accumulate, and the way they are accumulating is by shifting the mean of that distribution from which firms are drawing. And I mean, here we just recognize that that already happens today from the moment they innovate, right? And then we have this term in brackets, and this term in brackets seems is that we're going to allow for some cross-location diffusion in technology. And this seems like a wrinkle that why would you kind of want to add this on top of everything? And it's actually not, because of the following reason. You actually need that term in brackets in order for the model to have a well-defined balanced growth path. In order for the economy to eventually converge to a balanced growth path, you need some diffusion in the economy. Otherwise, some places just fall behind because they don't do a lot of innovation. But of course, you know, even places that don't do innovation at all, they get access to a lot of the innovations that have happened somewhere else in the world. And so this is supposed to represent this. Okay, so that's the production structure. And then finally, energy. So we're going to assume that energy is produced using fossil fuels and clean energy sources. They are combined with an elasticity of substitution production function that where the elasticity of substitution is governed by this parameter epsilon. Okay, and this epsilon is crucial. It's crucial for many things. We're going to keep it fixed here, but of course, it's very natural to think that this is a policy parameter, right? That you could change in principle with policy, and that it has dynamics, etc. So there's a whole agenda that you can build around this parameter epsilon, and some people, I guess, are getting into it. But we're going to keep it fixed for now. But you know, noted that this is an important parameter, and so this is the way you produce energy, and then the cost of the different types of energy is going to be governed by are these. So these are the unit the energy cost in units of labor, that we're going to allow this to depend on the way the frontier of knowledge is shifting. So the world economy is evolving because firms are investing in technology that leads to a growth model where the world economy is growing, right? That's the mechanism that we just discussed, right? And we're going to allow the cost of both types of fuels to be affected by the evolution of that technology frontier. We're just going to allow the rate at which that happened to vary by technology, by whether it's fossil fuels or clean energy sources. And we're going to choose those parameters so that the model matches the evolution of the share of both types of technology over time. Now, for carbon or fossil fuels, we're going to have this other term as well, this function F. And what is this function? What this function is trying to capture this idea that, you know, carbon is or carbon sources are a finite resource, that, you know, that eventually, you know, if I keep digging carbon or oil, it becomes harder and harder, more and more costly to get it. Okay, and so this is going to be kind of an increasing upward sloping or convex curve, capturing this effect, right? And there's some estimates out there of how big this effect is, and we're gonna use those. I'll show you those functions in a second, right? And so then we can put it all together. The equilibrium of the model, you know, has been analyzed in several other papers before. So there's the trade part that is going to lead to a gravity equation conditional on you know, bilateral iceberg trade costs. And then there's the dynamic part that given the structure that I show you is going to imply that firms are going to maximize their innovation. They're going to choose their innovation so as to maximize the chance of getting access to the land today, to be the ones that produce today, because the market for land is competitive. And so what that means is that there's going to be innovation, but this innovation is determined by that competition of land today. And all the rents from that innovation moving forward from tomorrow forward are going to simply go to the fixed factor, which is in this case land. And so the price of land is going to vary depending on how much innovation happens, but firms are going to decide on how much innovation to make depending on just what they need to do in order to win that competition for land. And so that solves the problem, makes a very complicated dynamic profit maximization problem, converts it into a static maximization problem, which simplifies a lot the solution of this model. Okay, so that's the core economic model. Let me talk about the climate part in a little more detail for a second. So as I said, if we saw the production function of energy, as that happens, there's emissions of carbon, and these emissions of carbon are going to accumulate in the atmosphere, and we're going to, like I said, use the IPCC 2013 model to make sure that we are kind of in line with what the scientists have told us about this process. Okay, so and I'll show you that we're very close to one of the scenarios of RCP 8.5 that they that they have produced. Now, once carbon goes into the atmosphere, it's going to affect the global temperatures, and now we have to also map those global temperatures into local temperatures at the level of disaggregation that we're using, etc. And so for that, we're going to use this paper by Mitchell. It's a very well-known paper that tells us how to downscale global temperatures into local temperatures. And what he tells us, and I mean, many people have used this before us, is that a good way of doing this is through this type of linear mapping, where there's a scalar function G that determines how global temperatures affect that particular location R. Okay, and you can estimate that G using a number of local characteristics, and so here's what we estimate that to be. So this is the temperature scalar, that G that I was referring to before. So in this map, you can see the level of disaggregation that we're using, which is kind of the pixels that you see in that in this map. But you can also see the range of temperatures or temperature changes implied by a 1 degree change in global temperature. So if global temperatures change by 1 degree Celsius, some of these areas here in the north, temperature increases by 2.2 degrees, while in some of, say, these regions in Central America, only increase by about a half. Okay, so very heterogeneous effects of global temperatures on local temperatures, and that's all captured by this G function. Okay, now I'll show you many different parameters. We try to be careful about quantifying all of this. Let me just emphasize one. That's the elasticity of substitution epsilon that I was talking about. We're gonna use a number that is kind of on the high side, 1.6, coming from these papers. But we play with this number a little bit, and there's certainly more room for research there, I think. Okay, then there is this function F that we talked about, the fact that carbon becomes more costly the more carbon you use. And so this is we're gonna go to this paper here that gives us the green points there. They've estimated, or they calculated the different cost of extracting depending on how much carbon has been extracted. And we're gonna fit the black curve to that. Now, the most important part, or one very important part, I should say, is how we estimate these damage functions, right? So these are the damage functions for amenities and productivities that I already described before. Here's the way we're going to do it. So we're going to take the model, right? And for a given period, the model, we can invert the model and obtain the productivities and amenities that make them all consistent with population counts and real local GDP across the world. Okay, so that is a unique mapping that allows us to recover productivities and amenities in a given period. We have 4 cross sections of for GECON, which is the data that we're using, which was produced by Northhouse and a team at that level of disaggregation that we're talking about, namely the 1 degree by 1 degree. And so that's going to give us a panel of 4 time periods, 5 years apart, of productivities and amenities in all these different squares in the world, all these different 1 degree by 1 degree cells. Yes, so that gives us this 4 period panel, and we're going to use that 4 period panel to estimate these damage functions. Okay, so we're already estimating on those fundamentals, right? So everything that the model captures, all the mechanisms that the model is capturing, they're already kind of, in some sense, controlled for when in these fundamentals. And we're gonna then take these fundamentals and run this type of regression. So this is the amenities that we're recovering in the way that I described, right? Once we also take out this whatever agglomeration or congestion force, local agglomeration or congestion force that we introduced, as I showed you before, and then we're going to run that, and we're going to run this type of regressions as you see there. So what does it, so this delta here, what is the concept of the delta, or how do you think about that delta? This is the semi-elasticity of amenities to 1 degree change, or 1 degree Celsius in change in temperature in areas that have temperature in this bin. Okay, and we're gonna get one by bin. Okay, and then we're gonna add location fixed effects, time trends, so some time trends at a slightly more aggregated level, and then there's an error. Okay, so we have local fixed effects that are going to be at the 2 by 2 degree level, and then we have trends that are at the subnational level. Okay, and so to try to saturate them all, and we're not get just from the basic distribution of or the spatial distribution of economic activity in the world, and the same for productivity. Essentially, we're going to make some small changes, but the idea is exactly the same. And so here's what you get when you do that. So on the left, I have the amenities. On the right, I have the productivities. The x-axis is January temperatures or July temperatures, depending on the hemisphere. And so what is this telling? This telling you is in the coldest places in the world, right, a 1 degree Celsius increase in temperatures increases amenities, say if you take the line, by about 2.5%. Okay, that's what this is telling you. And then that kind of goes down until it reaches 0 there, which is that, at that point, that's kind of the bliss point in terms of temperature for amenities, if you will. And then as temperatures get warmer than that, this region over here, then we start to lose from increases in temperatures. And in the warmest places in the world, you get about the opposite. So a 2.5% decline in amenities as a result of the extra degree Celsius. Okay, so that's what it's telling you. And you see something similar for productivities, a little smaller on the downside than the upside here, but the effects are larger. So a 1 degree Celsius increase in temperatures in the coldest places in the world increase productivity by about 10%, and decrease productivity by about 15% in the warmest places in the world. Now, as you can see, this type of methodology, this gives you clearly significant effects at the bottom, kind of in the coldest places, in the warmest places, both for amenities and for productivity, which is nice. It also gives you this very natural shape, right? That bad in the cold, is good in the very cold places, is bad in the very warm places, which is of course not imposed at all in that regression that I showed you. But there's substantial uncertainty about exactly the level of this, right? I mean, there's a lot of, we cannot pinpoint what's the optimal temperature to produce that well, etc., because the standard errors kind of here in the middle are quite big, right? And so that comes from the fact that, well, if we don't have a very long panel, but also, the effects of climate so far have not been that large to really capture, particularly in kind of in the middle range of places. But as I said, there's certainly some significant effects there. Okay, and finally, the natality rate. Like I said, we're going to make it a function of both income and the level of temperatures. For the level of temperature, we're going to follow this paper by Greenstone. And then for income, we're going to assume that it's a logistic form, and we're going to estimate it so that we kind of match the cross-section of the world economy. Okay. And so that's it. That's the description of the model. Should I stop for comments or questions or something, Frederick?
Yes, please. That would be great. So there are a couple of questions about the role of governments here. So let me just not make them more precise, the questions, but that's the agenda that is missing so far. So if you could dwell a little bit on that.
Sorry, I didn't.
So the role for governments there. So for instance, to tax CO2 emissions or to fix some of the other externalities that you have been mentioning.
Yeah. So of course, governments have a huge role here. This is a global externality, as we mentioned. I'm going to talk about policy. I'm going to talk about policy and the effect of policy in a little bit. So perhaps we should wait there. I haven't incorporated governments directly in the sense that they, in my baseline scenario, there's no real government action that is affecting these economies directly. Now, of course, in estimating trade barriers, in estimating migration costs, in estimating all of those things that go into the baseline of the model, there's governments behind all of those, of course, right? And so that is trying to capture, in a admittedly reduced form, the presence of governments in shaping the economy today. So now, of course, then there is the issue of, well, can governments impose particular policy on the economy, and what would be the effects of that policy? That's what I'll show you in a little bit. Okay.
Thank you. And there was another question by Marcelo on the impact on productivities. He says that they probably depend on the production bundle, but here production is only one good that is comprehensive of all the others, right? So it is Armington.
And it's Eaton and Corton, but could be written down in different ways. This is Eaton and Corton, so there's going to be different firms producing different varieties in a particular location now.
So maybe I'll let Marcelo rephrase his question, because I may have misunderstood what he wanted to ask.
So can you hear me?
Sure.
Okay. So it was just the point. I see that you have these differentiated products. My point was that maybe the impact on productivity is not the same in an economy that has 80% service production versus an economy that has 80% agriculture production. The increase in temperature will have different effects. I realize that you're not looking into this here.
No, that's a very important point. I couldn't agree more. And in fact, we have another paper that exactly does that, tries to understand what is the effect on the different sectors of changes in temperature, and then kind of trace differences in specialization that come as a result of the change in temperature. I think the challenge in doing that, I think that's an important channel, and that's why we wrote a paper on it. But one challenge in doing that is to estimate these damage functions at the sector level, right? That is a complicated task. it's, there's a question whether we have really enough information to do that, in a reasonable way. I mean, I think that's I think the key challenge to do that. Already in this, which is, as you correctly point out, for the whole output in a particular location, we're already stretching the ability to get numbers that are more or less precise that we can use in this. So that I think that's the challenge. And partly the reason we have this challenge is because the extent to which temperatures have been very relevant in determining, these switches in specialization so far is somewhat limited. And so that's, I think, now, of course, in the future, if this becomes worse and worse, as is predicted, I guess, there's going to be more evidence, and so we'll do a better job in estimating this. Now, of course, the methodology of these models you give me better data, I can refine these estimates and immediately produce better estimates also of the damages and cost and implications of the phenomenon. So I think this construction, in some sense, is not imperiled by that. Okay, continue. Okay, so let me show you some of the results. So the baseline, so this is the baseline scenario. It's where we start in 2000, like I said, and we're going to run them all forward. We can do it for as many years as we want. We're going to do it for 400 years. And what you see in the graph on the left is the green line is the evolution of CO2 emissions in the model. I have for reference two IPCC scenarios, the RCP 8.5, RCP 6.0. And you can see how in this quantification that we're using, we're relatively close to the RCP 8.5, which is an extreme business as usual scenario of the IPCC. So it's one of the most extreme scenarios that they have. Now notice that for them, at some point here in 2150, emissions start to decline. That's simply because they assume that there's an abatement technology that is coming and is going to solve this problem. For us, this is happening endogenously because the cost of extracting carbon becomes more and more increases as more carbon is used. Okay, and so you can see then on the right the evolution of global temperatures, and again that fits that scenario RCP 8.5 fairly closely. Okay. And so this, of course, is going to imply that both amenities and productivities are going to vary as a result of warming in the future. So what I have here is, what we are getting in the baseline relative to a world where we shut down global warming, so there's no warming, so that's a contrafactual world. And this is for, I just took a reference year for 2200, so that you get a sense of, what's the geography of these changes in amenities and productivities. And so you see, what you would expect, of course, that in the northern areas, amenities grow by about 30% in this case, productivity grows by about 80%. And particularly in the Central Africa and South America, amenities decline maybe by 20% or so, and productivity declines maybe by 50% or so, where the change in productivity also reaches kind of India and Southeast Asia a little bit more, and it's of course more pronounced because the damage function was had bigger effects as well. Note the rich world. So the rich world here, right? It's kind of at a cusp where it is not really that much affected in terms of both amenities and productivity. There's some effects; those effects are there and they're real, but it's kind of in between the parts of the world that are going to benefit in terms of both amenities and productivities, and the parts of the world that are going to suffer from it. Okay, and so this is going to have an effect on population through natality rates. it turns out that that effect is relatively small. It's about 30 million people. So climate is going to reduce the global population by about 30 million people, which of course, in the big scheme of population growth in the world, is a very small effect. And so that's why, it's hard to see the difference between these two curves. But, this also shows you the evolution of global population in the model, which is kind of within the range of what the UN has predicted, or at least up to 2100. And on the right, I have a map of the changes in population density by 2200 relative to a world, that counterfactual world without warming. And so the model predicts about a migration of about 600 million people relative to what you would have without warming. So lots of people, so that's a significant amount of people moving as a result of this. They move to those areas that are in red in the map, and are coming essentially from sub-Saharan Africa and parts of South America and parts of Australia and Southeast Asia, as I showed you for the amenities and productivity as well. So lots of migration as a result of this phenomenon. And this is just, if you put it all together, these are the effects on welfare. So the map shows you, the geography of them, but also kind of the range of these effects that go from minus about 15% to about plus 15%. So that's a huge range, right? So huge range in the increase in kind of inequality in the world as a result of this. And the right distribution tells you, this is the distribution of the welfare gains and losses, and you can see how that's like has two peaks. So one would be no effect, but more than one is positive effects for that area. This is all population weighted in the distribution, and so you can see how there's two modes there. One for the rich world that suffers little as a result of all of this, and one for these areas in Africa, etc., that are going to suffer a lot more as a result of this. And so, in some sense, the tragic of this graph is that all the losses here, all the dark blue areas, are concentrated in the poorest areas of the world that have also been areas that have contributed little to all of this phenomenon. And at the same time, the rich world here, so Europe, the US, mostly the kind of more northern part of the US, and Japan are suffering little, and they're all kind of in this part of the distribution. And then, of course, there's some places that win, but those places are places that today are not very highly populated. There will be more populated in the future as a result of this, but this is welfare as accounted for. What is the impact for individuals that are there, living there today? Okay, so if I trace kind of the dynasty of an individual that is living in that particular location today. Okay, this is a scatter of, if I relate real income per capita, say today in 2020, to the change in welfare from warming, as predicted by the numbers that I just showed you. And so you can see that there's a very clearly positive relationship between income per capita today and the effect that warming is going to have. So it's very negative effect for places that are very poor, and even positive or close to zero effect for places that are tend to be richer in the world. And so you can see the different colors are here are the different continents and or areas of the world. So red is in China, but I mean, look at sub-Saharan Africa, right? I mean, this is the yellow dots there. They are very, very badly affected at the very bottom of all of this. Okay. Now, of course, there's lots of uncertainty about these numbers. We don't know exactly the level of those damage functions. There's a lot of error in estimating them. And so what these graphs show you is, what if I take the kind of estimated logistic on those damage functions and then take into account kind of the uncertainty in those and filter that through the model, then you get, of course, kind of confidence intervals for the implications of the model. These are the implications, the aggregate implications of the model. And what this is telling you is, the 95% interval for 2200 is so the average loss is about, a little bit less than 10%, but it could be 0 or it could be 20%. So that's a big range, of course, for average. So it's not, there's some information there, of course, it's a big range. We are uncertain about the level of these effects. Now, on the other hand, the range of, who's going to gain the most, who's going to lose the most, that range of 30%, that seems to be more or less robust to the different scenarios that you can filter through the model. And so that 30% number is something that we think is easier to bring to the bank, in the sense that we're more confident that that number is the right number. So these are the distributions for the different levels of those damages. Okay, so I'm running a little bit out of time. So let me emphasize a couple of more things, and then I'll go through some of the policy exercises and conclude. So I emphasize the fact that there's this model has 3 main adaptation channels. It has migration, so individuals can move as a result of the area where they live being affected or more affected by climate. It has trade, and it has investments. And so in the paper we kind of go and analyze the importance of each of these adaptation channels. And so let me show you the one for migration, and then I'll mention briefly the other two. So what this exercise does is it says, well, let's do the diff and diff. So namely, what's the effect of climate, in a world that has high versus low migration costs. And so in this case, we're increasing migration costs by 25% in the map, and in the graph by either 12.5 or 25%. And what this shows you is that migration is a very important adaptation channel. So the cost, say by 2200 or a little bit later, is going to increase by about a third if migration costs were 25% larger. So if talking about governments and the effect of governments that Frederic was asking me about before, if governments come and shut down borders, right? What this is telling you is the cost grows significantly, right? Because you're taking away that adaptation mechanism for individuals. The geography of it is also kind of interesting because, of course, so the map is the diff and diff. So the red areas are areas that if you increase migration costs are going to suffer, or they benefit from having low migration costs. And so everything that is red are areas that, if you shut borders, it's bad for them. Why? Because, well, the northern areas is obvious because, they're benefiting from the migration into them. Now, for some other places, it's a little bit more interesting. The geography is a little bit more interesting, not as obvious. Like, for example, these parts of Africa. So what's happening there? Africa benefits from having low migration restrictions because that's the adaptation mechanism. The adaptation mechanism is move north, and if they move north, the locals are going to be better off. So that kind of makes sense too. But why is South America? But look at now at South America. South America and all the other maps that I showed you look very similar to Central Africa. But now it looks actually quite different. So why is that? Well, it depends on the density. It's all about density, right? South America is much less dense than Africa. And so if people start migrating out, it loses and the critical mass to do innovations and to develop its own economy. And so that's not so good for the locals. And so that they prefer a world with high migration costs in terms of the effects on climate. Same for Australia, for example. Okay. Now here in this world, trade doesn't play such a big role. And the reason is that, you know, the shocks are very spatially, the climate shocks are very spatially correlated, or the climate effects are very spatially correlated. And trade, of course, is very spatially correlated as well, in the sense that you trade much more with the places that are close to you. And so here, trade is not a great adaptation mechanism, but we don't have these sectoral changes in specialization that we were talking about. And once we've incorporated those in some of the rest of the work that we're doing on this, that channel has become is relevant, is more important, you know. And innovation is kind of in between. It's important, and it's particularly important in the long run. In the long run, it plays quite a big role. Let me finish with the effect of carbon taxes. So carbon taxes are, of course, super relevant as a policy option. Everyone talks about carbon taxes as the main solution that economists put on the table in order to solve this issue. And the logic is very simple. It's a Pigouvian logic, you know, just price whatever is causing the gap between the social value of carbon and the private value of carbon. Now, what we do in this paper is introduce carbon taxes, put it on all locations, rebate them locally, and see what's the effect on the economy. And so, as you know, as is obvious from imposing the tax, the CO2 emissions go down whenever you impose the tax, which implies that temperature increases are also going to go down. Now, the effects at the end of the day are more complex than that. And the reason they are more complex is the following, is if you consume less carbon today, tomorrow in the future, right, you're gonna have consumed the cumulative consumption that you've made, or that you've done, is also lower. And so what does that mean? It means that you didn't dig as deep in order to get carbon, which means that the cost of getting carbon are lower. And that undoes the tax to some extent, okay? That undoes the tax to some extent. And so that phenomenon implies that, you know, the effect of carbon taxes is like flattening the temperature curve. It reduces temperatures, but it reduces temperatures only in the short run. Or, I mean, here the short run can be centuries, of course, so it's not that short. It's a long short term. But in the very, very, very long term, eventually we consume the carbon. Okay, why? And so because there's this other effect that essentially kind of tends to undo the tax. Of course, you can always keep increasing the tax and do other types of policies, and studying those policies is interesting, but just the constant percentage tax flattens the curve. It doesn't reduce the curve permanently. And so what that implies is that if you want the carbon tax to be really effective, you really need to invest in technologies that eventually are going to solve the problem, that not only delay the use of carbon, but eventually, you know, can extract carbon from the atmosphere, etc. So they can abate the fact that carbon is in the atmosphere. So you don't only flatten the curve, but you also find a cure eventually, right? So very kind of analogous to what the arguments for COVID and infectious diseases in that sense, as you know. So carbon taxes flatten the curve, and that's particularly useful if a solution is forthcoming. Okay, so there's many other policies in the paper that we studied, the dynamic effects of these policies, clean energy subsidies, etc. I out of time, and I want to open for a discussion. So let me not go into those unless there's questions. And so let me just conclude. There's what are we doing? What we're doing here is, or the agenda more broadly, is to develop assessment models for climate change. We think it's crucial that these models have both a dynamic component and a spatial component, because the effects are very heterogeneous, and we need to understand the impact that heterogeneity is going to have, because it also leads to adaptation to both trade, migration, and even innovation. And these terms, what we find quantitatively, that this is extremely important both for the effects of policies and for the impact to individuals and ultimately the welfare losses that they're going to face. Thank you.
So many thanks, Esteban. We have a few questions from the audience. So Jeremy Laurent Luchetti was first. Jeremy? Are you still around? So maybe let me turn to Yuanzi. So,
okay, so first, thanks a lot for this really interesting and insightful presentation. I just have like one question, which is like, how do you think about like the effect of rising sea levels due to global warming? I'm just thinking like, you know, the major cities, for instance, in Norway or Japan, once we consider like the sea level change due to global warming, we might have like a very different distributional consequences of it.
Yeah, so that's a great question. We have, I mean, this framework is very amenable to that. I mean, that's another issue where, you know, the spatial dynamic component, it's essential. In some sense, the spatial component is even more important there because adapting by moving, even very locally, can have a huge impact on the losses. And so we have work where we've studied that in a related framework. And what we find is that, yes, it's important. It leads to a lot of adaptation. And what we find is that introducing that adaptation really changes the cost dramatically. Just to give you an idea, the cost, present discount the cost of flooding. So I should be precise about this. This inundation that we're talking about, right? Areas that are going to be underwater because sea levels are rising. Then there's another issue, which is like episodic events, so like storms and things like that. But just the part that is inundation, without thinking about adaptation and local adaptation, you would get costs that are about 4.5%. Once you take into account adaptation, you get to costs that are more in the range of 0.5%. Of course, it varies a lot by region. I mean, some cities are going to, you know, devastated, some others less so. But for the world as a whole, it's not such a big deal. I mean, well, 0.5% is not negligible, of course, but you know, because like I was saying, there's an easy or relatively easy form of adaptation, which is just move to areas that are not subject to this inundation. Now you can say, well, we've built a lot in areas that are subject to inundation, and so that's a problem. But there's one caveat to that reasoning, which is that this is happening, and there's the protracted part is really important. This is happening over hundreds of years, right? That we're talking about. I mean, or you know, or decades at the minimum, right? I mean, it depends on the speed and the scenario that we're thinking about. And you know, if we think over 50 years, which is a relatively short term for this phenomenon, right? You know, depreciation means that you're going to have to build all these buildings again anyway, right? So if you have the right policies to build somewhere else in places that, you know, are not subject to this, that cost essentially shouldn't be that large, right? And so that's essentially the issue. The issue is that it's relatively simple to move to other locations. Now, of course, there's things that, you know, we've invested and there's agglomeration effects in those areas, etc. So it's not as simple as I'm portraying it here. And so that's why you need a model to put it all together. And so that's what we've done.
Thank you. Jeremy is back.
Does not work.
Yeah. No,
sorry for that.
Yeah,
I'm sorry for that.
Yours.
Thank you very much for the presentation. I have a question regarding to the way you estimate the damages. So you estimate what happens in cell R, increase in temperature in this cell on damages and productivity in this cell. But
Yes.
we might think that what happens, increase in temperature in certain places will impact what happens in other places. For example, you know, increase in temperature in the pole might lead to sea level rise and impact coastal cities in the US. Can you account for this form of externalities between cells?
So we've tried to use different specifications, including specifications that have, you know, the effect on surrounding cells, etc. The problem is that, like I was saying, the effects of climate, at least in this kind of relatively short panel, are not that strong. And so the more complex you make the specification, the harder it is to really kind of get some of the precise effects. So that's why we've reduced it to some sort of very basic effects of, the temperature on the location to temperature to the effects on amenities. But in principle, of course, you can do that. We just didn't have a lot of success in getting kind of significant impact in these more complex specifications. But I think, that's a huge agenda, of course. Now, to try to improve on that estimation and introduce some of those effects. I couldn't agree more with you that, all these effects are very linked to each other. And not only that, but you can start thinking about like input-output linkages, etc., and how those, affect each other. There's all sorts of links that are important that make shocks or climate effects in one location affect other locations. So I couldn't agree more. I think there's an important agenda there. I think it's let me emphasize also the relevance of doing this on fundamentals, not on outcomes, which is something that I think has been done, but it can also be confusing and is not as useful for informing these models. But conditional on doing it like that, I think there's a lot of room to make these specifications more complex. My fear, to get the same answer that I was giving to Marcelo, is, do we have enough variation there to do it well already? Eventually, we will, sadly, but do we have enough? One source of variation is the episodic one, right? So the storms, etc., as I was saying, but there's a real question whether that, if you just use that variation, whether that's really what you want to capture, or you want to capture kind of effects that are more long-lasting and more permanent, and those can be quite different in terms of their nature and their effect on the economy. So I think there's many issues, but I think you identify an important one that needs more attention. We tried, didn't get more mileage, that much mileage, and so we just dropped it.
Thank you a lot.
We still have some questions. Not sure we will have time for them all. Fadi Hassan, if you can unmute and ask your question.
Yes, hi. Thank you very much for the presentation. My question is basically if you are capturing the impact on agriculture and on food production, especially, in the poorest areas. You already showed us that, there are the biggest welfare losses in sub-Saharan Africa and these types of areas. But I wonder whether if this could be somehow even an underestimate, given that, small change in temperature there might imply not being able, to have crops and have a large impact on food production. Is this something that you account for, or? Yes,
I could be. We try to. And to the extent that many of these areas in the world, a lot of the production, a big fraction of the population work in agriculture, the effects that we're measuring are mostly effects on agriculture. Note that the effects that we're getting are not small at all, right? This is telling you that in the warmest places in the world, an increase, a 1 degree Celsius increase is reducing productivity more than 15%, right? So that's a big negative shock to productivity. It's not a small effect, it's a huge effect, right? The reason then, but there's adaptation relative to that in the sense that not all cells or surrounding cells are affected in the same way, etc. And so that's what allows individuals in some sense to deal with this and not experience the full 15% shock, say. I'm just using a number, but the actual effect that we're measuring in the damage function is not small, it's very big, right? And includes in some sense everything, right? Everything that leads to individuals producing more or less in those regions. Now, there's another issue that or another way in which I can interpret your comment, which I think it's an important one, which is that, how far we're extrapolating from the sample that we have so far, right? So if temperatures really get a lot warmer, right, and in particular in the warmest places in the world, do we actually know, what's going to be the ability to produce in those places if they get even warmer, right? And I think you're absolutely right that well, this evidence doesn't help us with that, right? And so at the end of the day, you're using some functional form assumption to establish what would happen in those locations rather than actual data, because of course there's no actual data because no region has faced that type of temperature. I mean, I think that's a problem for our estimate, but it's a problem for any estimate that is not about mechanisms, right? So of course, agronomists can come and tell us, look, this is it. You cannot harvest anything there beyond this temperature. But even then, I would argue, I don't know, there's innovations and there's different types of crops. And I mean, there's different ways to react to that. But you're right that we have a lot less information in those extremes and what would happen in those extremes, particularly in the warmest areas in the world. But I really a little bit at a loss how we could do that, at least statistically, without really going into the particular mechanisms that we have to produce in very, very warm weather.
Thank you very much. So sorry, we ran out of time. So for the remaining questions, please maybe send an email directly to Esteban. So many thanks, Esteban, for this excellent presentation and great paper, and also to the participants who joined us today. The next seminar will take place on October 18th, and the speaker will be Penny Kohlberg. So thank you very much again, and have a good day in Chicago and elsewhere.
Thank you.
Thank you. Bye.